Yeah, hello everybody, welcome back to our lecture on polymer science and processing. We are now approaching the finishing line and are really going into the realm of polymer processing. So before we start, a quick recap of last lecture. We already started to discuss one way on how to process polymers, and in this case to process them into polymer nanoparticles. And then we see that there's a couple of applications. Keep them in mind. One important one is dispersion paints, which will pop up again in next week's chapter. And apart from this, we discussed on how we can synthesize polymer particles, for example by emulsion or mini-emulsion polymerization. And then I showed you a couple of tricks on how to make more complicated architectures, nanocapsules, Janus particles, Korshell particles, and so on, just to give you a bit of a flavor on what can be done with such polymer nanoparticles. Now in today's lecture we really want to go into real engineering, and our mission should be to understand how we can make all these polymer products we know from everyday life. So again, if we go to our overview of the course, you see now we came full circle. We went from polymer chemistry via polymer physics and materials to polymer processing, and our task for today will be to make a direct connection from the chemistry into a product. So what needs to be done once we have the polymers to make them into a product? And if you want simplistically speaking, it's fairly clear. So the process chain is we start with a monomer that can either come from renewable sources or maybe from petrochemicals like ethylene. Then we polymerize this, and we learned a lot about polymerization techniques at the very beginning of the course. And then we will formulate this to make some kind of a crude product, which is typically a polymer granulate. This will typically be done by extrusion, is one of the key techniques that we will cover in this week's lecture. So this is what you can buy if you are a company from large chemical companies that make such polymers, and then in your specialized company, your task will be to convert this crude product into any type of really end product, whatever you want to do. Now, and this requires different processing techniques and possibly some kind of conditioning and so on to really make what you want to make with this crude polymer granulate. And in today's lecture, we want to look at these processing steps that we can apply in order to kind of reform this polymer granulate into normal structures. Okay, and of course there's a lot of different ways on how one can categorize these processing techniques, and of course it's also, I think, clear for everybody that there's a big range of different processing techniques to actually manipulate polymers. And the reason for this is that it's actually fairly easy to manipulate polymers because they tend to easily melt, they can be dissolved, they can be processed in other ways, and so on. No, they can even in solid state you can amend them. And what I decided to do here is to categorize or to sort these different processing techniques according to the state of the polymer, so what we need to do the polymer to reform them. So there's different ways on how we can use a polymer. We can use a polymer in a melt, so a liquid type of polymer. We can use a solid type of polymer, but we can also apply the polymers in different, if you want, forms, either as a solution in a solvent, so single polymer chains surrounded by solvent molecules, in a dispersion. This is what we covered last week when we discussed nanoparticles, so small polymer particles surrounded by a non-solvent but a liquid continuous phase, or we can apply them as a dry solid powder. And all of these ways on how we can make a polymer will find processes in order to form them into a final product. And here's just a huge overview of important techniques. This is by far not complete, of course, but some, if you want, archetypical processing techniques that somewhat convert these different states of the polymers into a product. You see, this is a lot of things, and what we will do in the next two lectures is to walk slowly through these categories and then discuss individual processes in detail. And today we want to cover melt processes and a little bit of solid state process. So mostly we will look at extrusion, injection molding, and blow molding, and maybe foaming, so how one can make foamy materials, as these are, if you want, very basic principles on how a polymer can be processed. So just for you maybe to think along a little bit, extrusion is probably the key or the basic processing techniques of polymers. And if you think about extrusion, is there any material that comes to your mind that has been prepared by an extrusion process? So take a second, think about this. What kind of materials or what kind of polymer materials can we make by extrusion? Well, very typically, pipes. So extrusion is a process that creates really long chains or infinitely long materials that have a certain cross-section. And pipes is one particular example of this. Then extrusion is also used, as I already said 2 slides ago, to make granulates, compounds, and so on. So all these, if you want, crude polymer products that we can use to actually then reform by our defined techniques. No, this is what you buy from really big chemical companies if you want. But there's more things that can be done by extrusion. One very common thing that is disappearing more and more from our daily lives, which is a good point, is plastic bags. No, they create a lot of waste, but of course they are also very lightweight, and it can be a very efficient way to transport materials and to create packings without having to carry more weight, which also consumes energy if you carry them around for a long time. So plastic bags, whether reusable or just single-use plastic bags, are also done by extrusion, and this is also what we will cover in a little bit more detail in a second. And finally, any kinds of plastic wraps. So these typical wraps that you use to put your food that you have not finished back into the fridge, or that you can apply on much larger scales. If you remember back from the, I think, 2000s or so, when Christo wrapped the German Bundestag, you could see, this is all these. The wrapping itself was produced by an extrusion process. Okay, injection molding. This is probably the most widely applied type of polymer processing, and I'm not sure if you're familiar with the process, but I'll give you a couple of examples what can be done by injection molding. And before I do so, I again invite you to think about what can be molded with a polymer. Well, and the answer is pretty much everything. It's also something that we will see in more detail. A lot of car parts are produced by injection molding. Bumpers, for example, plastic parts, the inner plastic parts of a car. Any kind of plastic household items, whether this is disposable cutlery or cups or plates and so on, they are typically injection molded as well. Anything related to electronics, or if you want the cover for electronics, such as radio shellings or like the good old Game Boy. This is something that I grew up with. And a huge range of toys, so pretty much any plastic toy, whether this is Lego bricks or Playmobil figurines or whatever this could be, is all fabricated by injection molding. So the next thing we want to cover in today's lectures is a so-called blow molding process. So this combines injection molding with some kind of blowing up processing step, and this is how you make plastic bottles. So any plastic bottle that you may have next to your desk while you're watching this video or in your fridge or wherever is done by this blow molding process. And then there's a bit of a kind of speciality of this, and this is thermoplastic foam injection molding. So a bit of a bulky process name, which is typically known as foaming. And this is how we create all these materials that consist of foam in our material. And this could, for example, be boxes. So you order food, because right at this moment in the pandemic, you don't have any other choice than to order food. And very often it comes in boxes. And sometimes these boxes are made from Styrofoam. Not very often anymore, again for a good reason, because you want to save products and save polymers and do something that is more reusable. But of course, Styrofoam also comes as kind of wrappings for if you buy a new TV or whatever, to make it shock resistant so that the TV doesn't break while you bring it to your home. And maybe even more importantly, because you're healthy, you ride your bike to work or for exercise, you typically wear a helmet, and bicycle helmets, the cushion part of the helmet is also done, this one, by injection foam molding. And then at night, after a good bike ride, you get tired, so you take a nap, and you take a nap typically on mattresses. And mattresses, again, is one of the other really big product that consists of a foam. And I mean, we all know how important it is to sleep well, and this pretty much relates to the quality of the mattress, which can be tracked down to the properties of the polymers that mattress is composed of. Okay, so you see really a big variety of items you use in your daily life are fabricated from polymers by one or even multiple of these processes that I just introduced to you. And now what we want to do is we want to take a step back and look at all these processes in a little bit more detail. And what we start with is the extrusion process. So the principle of extrusion is actually fairly simple and can be very easily pictured by this picture here. So you see, this is Play-Doh, and what you can do with these Play-Doh machines is you put the soft Play-Doh in here, then you push, and this pushing will bring the Play-Doh out of this little die here, and then you can have this selection of, if you want, die shapes that will then extrude a polymer or a Play-Doh tube or line or star-shaped or whatever this may be line from this very basic extrusion device. So this is exactly how all these big polymer products are made as well, only that you try to avoid manual pushing, and of course use a bit of a more sophisticated upstream processing, but the principle here is exactly the same. It comes out through the die shapes the form, and then it comes out as an infinite long string. Okay, so again, in a bit more detail, the fundamentals of extrusion is we have a crude polymer. This is something we can either make ourselves or we buy it from a company. And this is heated and then homogenized and finally melted within this extruder or the extrusion machine. And this polymer melt is then pressed through a die with a desired cross-sectional shape. That's exactly what we have here. Oh, this is what this Play-Doh machine also does. And then once it comes out, the polymer starts cooling, and this polymer exudate then obtains a defined cross-section that is given by the cross-sectional shape of the die. So you see, the biggest advantage of this extrusion process is that it's continuous. So you can run it over and over and continuously, and you put your feedstock at one side and you get your product or maybe crude product out at the end. And it gives compounds, and they always have an infinite length. Now this is kind of by the very nature of this continuous process, that's what you would expect. And now you can, of course, cut it into defined lengths and shapes and so on. And what you can do from this is tubes, pipes, strings, but also plates, if you make a very thin cross-section, or foils, if you then blow up your cross-section to really thin out the layer material. So that leaves the question on how do we actually achieve this heating, homogenization, and melting. And in order to do this, you see a very schematic illustration of such an extruder. And you see you have a feed here. So here you add your material. You have a screw, and this screw now rotates to bring your polymer granulate towards the die. And as it goes along, it heats up. And there's two ways on how it is heated. Firstly, we have external heaters, and secondly, we have a specialized shape of this extrusion screw here. Okay, and this is what we will look at in a bit more detail. So here again, you see the cross-section of the screw. And you see, in the beginning, this is where you have your polymer granulate. The cross-section here is relatively small. So in this entry zone, we have solid particles as the raw polymer product. And they are firstly mixed here. If you want to have multiple polymers or whatever, different colors and so on, here you can mix them and homogenize the powder. And at the end of zone 1, we try to get the particle temperature above the glass transition temperature. Because what we need to do is we need to soften our material and eventually push it into a melted state. So in the next part, in the middle here, we see that the cross-section here, the thickness of the screw increases. And as you increase the thickness of the screw, you leave less volume for your polymer granulate. And that means that you have, as the polymer granulate is transported into this, along the screw, there will be more and more friction as you have more and more collisions between the particles. And frictions or collisions causes an increase in temperature. Now this is if you think about collisions of molecules, this is the very definition of temperature. Now how many molecules you are hitting your skin at a certain time determines on whether it feels warm or cold for you. And that's exactly the same thing for these particles here. So you increase the amount of contacts, that increases friction, and that increases temperature. So that's exactly what you see here. We have a higher pressure, we have more collisions, and then we get heating. And at the end of the zone here, the heat that we have supplied is large enough to actually really melt the polymers into one viscous liquid-like form. And this then goes to the metering zone, the end. So here we homogenize the melt, we can adjust the viscosity or the temperature so that it comes out of the die in a very well-controlled fashion. And it ends in this die, what you will see here, where the polymer then comes out. And just to give you a visual kind of illustration of this, here's a kind of short extraction of this melting zone and the close-up of the melting zone. And you see that while the particles here have relatively large volumes, as we push them forwards, they start to become more and more compacted and more heated by friction, and this brings or induces this melting process. And typically, maybe a little bit unexpected, from this heating, you still have these two contributions, external heating from the outside of the extruder, and if you want internal heating by friction, and something between 60 and 90% of heat is actually provided by friction. So this internal mechanism is actually the dominating factor. And here I really need to say a big thank you to Bill Hammack, who owns a YouTube channel known as Engineer Guy. And if you tune into this channel to see, he has really good explanations on how a lot of different machinery works. And he very kindly allowed me to use his very beautiful cartoons. You will see much more of them in my lecture as well. So Bill, thank you very much, much appreciated. And I think also for all of our listeners and students, they will also appreciate your very nice illustrations. Thank you. Okay, so this is generally how we generate this soft, dewy, and viscous polymer melt. So now, of course, there's a lot of different polymers, and we discussed this at length, that the glass transition temperature of the polymer, or if you want, the resistance to polymer chain movement can vary dramatically. Now think about the difference between a very soft rubber, polyisoprene for example, and something very hard, let's say something like Kevlar, if you want to go to the extremes, that literally doesn't melt at all and is very stiff and shock absorbing. And of course, in your extrudate process, you somewhat need to accommodate for all these different types of thermal behaviors of polymers. And that means that there is hardly a one-size-fits-it-all extruder that can process any type of polymers. And what you need to do is, if you want delicately balance this friction that you supply to either be very mild when you have polymers that tend to melt or become soft very easily, or to apply more and more friction for polymers that have a higher glass transition temperature and therefore are more resistant to becoming soft. And this can be very precisely adjusted by so-called twin screw extruders, where you have two screws that can either rotate in parallel or rotate against each other. And depending on how you adjust this, so if they rotate against each other, of course you create much more friction because you induce more and more collisions, and you can also adjust the distance between the two to make it either easier or harder for the polymer material to melt. And this allows you then to, first of all, increase the mixing or the efficiency of mixing, the efficiency of heat transfer, and also to treat more delicate powders where you actually may risk to destroy the powder if you apply too much friction. So these twin screw extruders are a very good tool to delicately play around with these structures. Okay, so now at the end of this extrusion process, we have a polymer melt that is homogeneous. The viscosity is adjusted in a way that it comes out of the die in a somewhat regular fashion. And then we approach the exit. So we see here's the extruder. We go through some parts where we can have filters, for example, to remove any impurities and adjust the viscosity while it approaches the die. And finally, it comes out of these die lips to get a defined cross-section. And here is now one thing that we really need to consider given all the knowledge of polymers that we have obtained. In order to show this to you, let me move to the blackboard. So now we assume we have a polymer melt that is somewhat funneled into this die here. Here's the extruder. And here are polymer chains. And we already know in the polymer chains, we established already they are in a liquid-like state, so a viscous polymer melt. And we already know from lectures that are far off, when we talked about polymer physics, that polymers always like to be in this random coil position. And why do they like to be in the random coil? Think back to one of the last lectures, or a few lectures back. And the reason is because this is entropically favored. There's the maximum numbers of microstates is achieved for this random coil configuration. So now this random coil configured polymer approaches the die, and because the die is very, if you want, thin, it is squeezed at high pressures through the die. And similar to, if you think about logs or anything that is in a river, the polymer, if the river becomes smaller, the speed becomes higher and things tend to align along the flow direction. So also the polymer, as it goes through the die, will tend to align in direction of the flow. So now they come out of the die, still aligned. And while they are still in a viscous state, or it takes some time for them to cool down, they experience that now there is no confining element anymore. And now the polymers realize, wait a minute, this is not really what I like to be in. I don't really like to be in this stretched out conformation, and entropy tells me to please go back into my minimum energy state, which is a random coil. So what they will do as they come out after pretty much directly after this external pressure is relaxed, they will start to coil up again. And as they coil up, of course, we change the cross-section of our exudate that comes out. Because now this exudate will expand perpendicular to the extrusion direction. Simply because the chains that have been aligned here, if you want, pop up. So it expands the cross-section. And this process is known as extrudate swelling. Now, as very often with physics, there's things you cannot avoid. And this is just a basic phenomenon that will always occur. You cannot fight, or it's very hard to fight minimum free energy. Of course, you can try to cool it as quick as possible and so on, but there will always be a tendency for the system to relax in a ground state. When you force it to a die, you cannot do anything but to somewhat live with this exudate swelling. And again, as very often, if you cannot fight physics, you need to learn to live with it. Now just remember from last week, when we talked about polymer nanoparticles, we know there is van der Waals forces, so we need to do something to somewhat counteract these forces and to prevent a particle dispersion from agglomerating. In that case, we use charges now to create electrostatic repulsion. Now here we need to find a more engineering type approach. So as often in engineering, if you cannot change something or if there's a problem, and you cannot solve it, you need to live with it and you need to somewhat work around it. And what you can do to prevent not the effect itself, you can try to prevent the consequences. And what you can simply do maybe fighting is not the right word because in effect you don't fight it, you live with it. What you can do is, let's say you want to have a square cross-section. Now this is your die here. Now your polymer comes out here, and as it comes out of this cross-section, what it will do is it will pop up and you will end up having such a cross-section instead of the square one. So if you want to have a square cross-section and you know how much your material extrudates, you can simply maybe. So this is the die cross-section. If you know that it will swell up, you can simply change the shape of your die. And if you now shape your die in a concave way, then it will swell up, but it will swell up into your desired cross-section. And this is what you do to overcompensate or to compensate for this extrudate swelling. So actually we don't fight it, we compensate it. Okay, so that's what you see as well. And here you see this maybe a little bit more beautifully. If this is your profile, it will swell up. So you make your profile concave, and then it will come out straight. Okay, so this is pretty much what I want to discuss in the context of extrusion. And now I show you two typical processes. As I said, there's a lot of materials or a lot of shapes that can be produced, maybe two somewhat specialized ones. The first is how we can make foils. So foils will be either used as wrapping foils or as plastic bags if you then merge them together and so on. And in order to do this, we somewhat need to find a way on how we can expand the material as it comes out of the extruder. And what we see here is we have our extruder. You see the shape of our screw again. Here the liquid polymer comes out, and now instead of having a solid cross-section, the cross-section here is a hollow ring. So it comes out in a ring-like fashion, and then we blow in air in the middle. This air will expand this cross-section more. As it expands, it thins out the polymer material that comes out of this extruder, and then we create this huge hollow tube that is subsequently being collected here, and then it goes along, and at the end of the day, it's just being wrapped up. And this is how one makes foils and plastic bags and so on and so forth. A second example, here, by the way, you see a close-up image of such an extruder. You see here is where the polymer comes out, and you see here is kind of an outlet to blow in air, and this then, as you see, expands the cross-section, thins out the material, and this is how you produce these plastic foils. Okay, another thing that is also done by extrusion, which may not be as intuitive, is the electrical insulation of wires. Now, anybody that has installed, let's say, a light bulb in his or her life knows that copper cables that are used for electricity are typically or hopefully covered by a plastic coating to prevent you from getting electrocuted while you touch the cable. And how to do this is actually fairly simple. Again, we have a machine that operates by an extruder. So again, in this case, the extruder is schematically shown from top to bottom. So we use our screw, we melt our material, and now we flow our liquid polymer along this channel. And while it comes into this cross-section, we see that you have an empty wire that is being kind of pulled through the extruder. It goes here, enters the liquid polymer, and comes out as a coated wire. So also here, I mean, wires are also produced at infinite length, and it only makes sense to produce this or to coat this with the same process that also changes the cross-section or the chemistry, but just continuously coats the material. And this is how it looks like in real life. Here is our wire that comes into this extrusion machine. So this is kind of the extruder. And here the liquid polymer is being inserted, and out comes the wire coated with a polymer coating. And this is, in a nutshell, how extrusion works. So next, I want to move on and discuss injection molding a little bit. And injection molding, again, has a very simple principle, and that you can see here. We have a soft polymer material, or typically a liquid polymer material. We push it into a form, and as we release the form, we have our polymer in a desired shape. Okay, so the fundamentals of injection molding is that we need to, again, heat, homogenize, and liquefy our polymer, and we do this using the machine that we already learned to appreciate, an extruder. And now, instead of having the extruder run continuously to produce infinite length materials, we actually just use it as a way to heat up the material. And then we fill this polymer melt into a desired form, similar to our Play-Doh material here. And we press the form together to create a three-dimensional object and let the polymer solidify by cooling. And as it cools, we can open the form and eject, using some hydraulic ejection, we eject our polymer material. So you see, in contrast to the extrusion process, this injection molding process is a batch process. So there's always a cyclic operation. You continuously fill in, squeeze, and eject your material, and then you restart again. And often, to save time, you try to create multiple objects within one single batch, to simply number up your throughput. And these can be connected via small tubes, so to kind of equally distribute the polymer or polymer melt flow. And now you can imagine, since you can make forms in any kind of shape, size, structure, and so on, you have a tremendous variety of different forms, different choices, and so on. And this is why injection molding is, I would say, the most widely applied methods to process polymers. So now, how does this look like? Here you see a very complicated schematic of such an injection molding unit. And without going into details, let me just pick out some things that should look familiar to you. So here we have an extruder. So we see here in the hopper, we feed in our polymer granulate. It's being transported in this direction. And this just heats up the polymer. And then we have two more units. One is the injection unit. So this is pretty much something that pushes the material in this direction so that it can enter the form. And then we have the clamp. So here is where we inject the mold and then cyclically press together and remove. And now I will show this to you much more schematically. And again, thank you very much for Bill Hammock, who will now pretty much deliver all the cartoons that I will show you to explain the process. Here, much more schematically, we have our injection unit. That comprises the extruder, the feed, and then some kind of hydraulic system that pushes the extruding screw back and forth. Then we have our mold structure here, and we have a clamp that can be opened or can be used to open and close this this mold, so that we can either form something or eject it. Okay, and now we will walk through these different units and try to understand or get the gist of the most important criteria that are involved in their operation. So the first one is the injection unit. And this now goes back to a very interesting effect of the extruder, and that is the heating from the inside. So historically, when you want to make polymers, what you needed to do is you heat the coating from the outside. So if you want, simplistically speaking, you put it in the oven, you apply heat from the outside, and then you fill it into a form and create something. And at the very beginning of polymer science or of polymer materials, this is how polymers were processed. But now here's a big problem. The temperature profile is non-uniform. If you heat from the outside, you always have a region that is cold in the interior and a region that is too hot at the outside. And that phenomenon is very familiar to anybody that likes to go camping. That's the bonfire effect. You burn your face, but your back still freezes if you sit in front of the bonfire. Same for the polymer here. one side burns, the other side freezes. And that's of course a huge problem because either the polymer is not liquid enough and not viscous or not flowing enough to be very efficiently injected, or it becomes too hot and then it can suffer and degrade. So either it changes color or it changes properties or it starts to burn in the worst case. And that has been a tremendous problem to make reliably and cheaply polymer products. And now here comes the extruder. Now you have this reciprocating screw in the extruder that, as we discussed, heats from the inside by creating friction and from the outside by supplying external heat. And that means that we have a homogeneous transport towards the nozzle because we have a homogeneous temperature profile. And this then allowed to do very precise engineering and forming of polymers. So this screw here, which sounds so simple and almost kind of neglectable, is at the core of a reliable polymer processing. Okay, so now I said it's just an extruder. It's actually not exactly true. There are some key differences to a normal extruder because we need to convert from this continuous operation to this batch-wise operation. So instead of a continuous rotating screw, we have what is known as a hydraulic ram. So how this works is the following. Here's our screw. And now we have two additional parts in this material. Openings that are known as flutes, where from the outside of the screw, liquid polymer can be filled into this injection unit, so the very front of the material. And we have these check rings, or these two rings, thrust ring and check ring, that can selectively open and close the front part of the material. So you can imagine as the material is being transported forward, it flows into this chamber here, and from there it flows into this chamber here. So it fills up completely. And now, as this hydraulic ram pushes forward the entire extruder to inject the viscous or the liquid polymer into the form, you need to ensure that the polymer is actually flowing in this direction into the form and not back here. And for this you need to have the selective opening and closing effect. And how this is realized here is that you have a ring on the screw. As you push forward, this pushes towards the check rings. So now you prevent flow in the wrong direction. And now the entire unit can push forward and deliver all the liquid polymer from the top into the form. Okay, and this is a key difference to a normal extruder where you just have a screw that keeps on turning and delivers the material towards the die. Okay, so now, having established how we can fill the form, let's do it. So we use our mold here, our form, that is filled by the injection unit. So you see, now it's full. The next problem we need to consider is that the mold doesn't exist in a vacuum, but is already filled with air. And now, if you think about this, in order to efficiently and really reliably produce this polymer material, you need to ensure that the air goes out so that it can be replaced with a polymer. So where does the air go? Well, very simple. We need to drill in small holes, so in order that the air can escape. So our form has these small ventilation holes. So the next question is, why does the polymer not escape? Well, here again, this is an engineering problem. You need to make sure that air with an extremely low viscosity can go through these little pores or these little openings, but the polymer with a very much higher viscosity cannot. So you simply need to play around with the injection pressure and the size of the holes. And then you take advantage of the different, if you want, flowability of the two materials. Well, and finally, we need to make sure that the polymer, once it's injected into our mold, is cooled so that we can take it out as a solid material. And this is realized by simply kind of water pipes where you flow cold water and then solidify your material that you want to form. Okay, so how does the clamp then work? So first we inject. You see here, this is the injection unit. This is the form that we want to produce. And now this can completely withdraw and then open the form. And then you have this ejection unit where you have kind of 2 or 4 or however many kind of small fingers that then push out your finalized form from this ejection unit. And this falls down, this can close again, and then you're ready for the next process. And because you have these ejection unit, it's fairly easy to find or to trace the injection molding process to products or polymer materials that you may have in your daily life. So what I would invite you for is now hit pause, take a look around your apartment, your room, your kitchen, your desk, and try to find something that you would suspect is being made by an extrusion process. Little hints, this laser pointer here will have been made by an extrusion process, the plastic cover of your cell phone, a lot of whatever electronic materials, probably your pocket calculator, maybe the backside of your laptop, your kitchen chair, if it's from plastic, and all kinds of whatever, different kitchen equipment, and so on. Your toothbrush, they will all be made by injection molding. And now try to find indications that this indeed is the case. And the hint is that we need to look for these, what is known as ejection marks. Now they come out of a relatively hot polymer and you need to apply some force to keep it out of the mold. So sometimes or often you see imprints of this injection molding process. So here you see in this very cheap toothbrush, this one here is an ejection mark. And here in the cheap garden chair, I'm not sure this is easily visible, but you see that you have these really big 1, 2, 3, 4, and so on patches. Here is one as well, that you can see where this garden chair has been pushed out. So if I open, for example, my laser pointer here, this is not something that you will be able to see, but you will, if you have something like this at home, you will very clearly see these ejection marks in here. Or maybe I can even, Reza, if you want, I can also zoom in. I'm not sure if you can actually see this. Oops. But if you look closely, you should be able to see a few regular marks kind of on the sides here as the ejection marks. Okay, Reza is nodding, so it seems we can see them. If not, please look for yourself. You will see this in pretty much more, or maybe not all, but most of the polymer materials you have in your house. Okay, and this is a telltale sign that this has been produced by injection molding. Okay, so some process considerations that I would like to discuss with you shortly. One is known as the sprue formation. So often, if you mold something, you have like a big plastic part that is still a remain from the nozzle. Because at the nozzle, you inject, but then the polymer cools down, and it may stick to your fabricated part. And what you need to do then is to polish it off. So you cut it off, and then you polish it, and then you have your final part. But sometimes, especially if you operate such things at very high throughput, you cannot afford to manually kind of shape each object. And for this, you need to kind of look into the process in a bit more detail to find ways on how to circumvent the solidification of this nozzle part. And there's two options. One is that you disconnect the material you want to prepare from your actual injection unit. And this can be done via so-called runners. So you see here, if you want to produce multiple objects, what you do is you make a form that's a bit more complicated. But now, here you inject, and then it goes via these runners to all these individual objects. And then at the end of the process, you still have to cut the objects from your runners, and then whatever remains as a material, you can put it back into your extruder if you want to save the material. And now if you, for example, buy a new board game that may have plastic parts, you very often see that all the plastic parts are somewhat connected in intricate pattern. And this is simply the remains of the extrusion process, and they leave it up to you to really put them or separate them and put them together. Now this is, I think, something that a lot of people will have experienced already. Okay, but yet somebody needs to stitch them off, and sometimes the company will leave it up to you to do, or they can do it themselves. But still, if you really prepare something in large quantities, that's still not a good solution. So in order to do it even better or even more efficiently, the second option is to completely avoid that this sprue will solidify. And in order to do this, you heat up the runners. So as the hot polymer comes from the injection unit and is distributed via these runners into your plastic, if you heat these up, no, as indicated by red here, the sprue will never become solid, but it will remain liquid and will then pull the liquid polymer apart, and you get a fairly clear cut here. And this is a way on how you can produce multiple objects at the same time without having to worry about kind of impurities and inaccurate shapes of the material. And this is, for example, how Lego bricks are made. Because for Lego, you really need a lot of bricks, and you cannot afford to have any impurities, otherwise they will not stick well, and then you need to work with these hot runners. Okay, similarly, there's another complication, and that complication is known as the draft angle. And this can be fairly easily explained by the following consideration. Let's say you shape something, you want to make, let's say, a bucket, and if the bucket has perfectly straight walls, as you try to move out your form, your mold here in this direction, you suck a vacuum here. And that will make it very difficult to completely separate your filled out form or your product from this form. So if the walls continuously touch, first of all, you have high friction, and secondly, you do not get air in, and that means you need to work against vacuum, and you cannot break it easily, and that's a problem. So how to avoid this? Now maybe take a second to think about for yourself. Let's say you designed these beautiful forms or molds to make buckets or so, and then you see it never comes out of the form. How do you solve that problem? How do you get air inside? Well, you could drill a little hole, but then your bucket will have a hole. That's maybe not recommendable, but you can slightly change the angle of your system. So see here, now maybe a little bit exaggerated, if you taper the walls and don't make them perfectly straight, but a little bit kind of opening, as you move your mold out a little bit, you start to open up air channels that run all the way to the interior, and that allows air to flow in, and then you don't have to, or you break the vacuum very efficiently, and that means it's much easier to separate. And of course also you eliminate friction from pulling out. So that is the most efficient way on how to design your material. So now you may say, wait a minute, let's say we make a Lego brick, then this is all nice and beautiful, but it needs to have straight walls, otherwise I cannot play Lego. No, Lego relies on bricks that are very rectangular in shape and very straight, otherwise you cannot build a nice wall, house, Death Star or whatever you want to play with Lego. And that is right, but a Lego brick only needs to be very square at the outside. And now if you have a look at the Lego brick, you see here, outside is perfectly square. But if you cut it open, you will see that inside you actually have a slightly tapered wall. Nobody cares because you don't use the inside of a Lego brick. You're only interested in the function from the outside. But here, they encode this trick to easily separate the brick from the mold. Okay, so next, polymers shrink. And we notice all materials shrink when you cool them down, no, because they solidify. And if they crystallize, this may shrink a little bit more. It depends, very generally speaking, on the type of polymer, on the crystallinity. No? When it comes from the melt and it crystallizes a lot, and of course you consume more volume because the crystals pack more efficiently. But it also depends on the external pressure, the temperature, and possibly the addition of fillers to mitigate that problem a little bit. Now, and you see, then you can find in literature these diagrams that tells you how the specific volume relates to temperature. And what you see here is that it depends on the applied pressure. No, because if you put a high pressure from the outside, you prevent a little bit this compression or this expansion at high temperatures. So you see at high temperatures, polymers expand because the chains move and rotate freely, and this increases the specific volume. As you cool down, this stops more and more. And then once you overcome the glass transition temperature, it very rapidly cools down. And now it depends on whether you cool fast or slow. We see the specific volume makes a difference. So what you want to do is you want to cool down fast to prevent the polymers from really packing efficiently, because this prevents shrinking. And you want, or if needed, you can apply external pressure from the outside to prevent the polymers in the melt to occupy as much volume as they want, no? Because you squeeze them together from the inside. Now it depends a bit on your criteria, on what you need to do to your extruder and to your polymer and potentially to the addition of your polymer to come up with a shrinkage that is within the norms. Because of course if they shrink too much, then your form doesn't fit and so on, or you change the properties of the final material. And just to show you how much shrinkage is to be expected, you see different polymers here, and you see that the shrinkage depends from, let's say, a few percent, 3% to very little. And now if we take a closer look at these things, or maybe this is something that you can do for yourself, try to rationalize why does PMA only smell, or polystyrene, only swell a little bit, and why, for example, polypropylene, polyoxymethylene, nylon, and polyethylene shrink much more upon cooling. And then try also to answer why this is given as a range and not as a precise number. If you think about this, you have understood how these polymers behave in their thermal processing window. And if not, go one slide back and try to recapitulate what I explained there in terms of this shrinking process. Okay, so now you can take all of this together and you can come up with a processing window. And in this processing window, we take up two parameters. So we have an injection temperature, and on the x-axis, we place our holding pressure. So this is the pressure within our machine or within our mold, and this is of course the temperature of the polymer melt. So now we have, in terms of temperature, we have two things to consider. We can have a temperature that is too low, and when the temperature is too low, then we do not fill our form completely. And this is known as a short stop. So we do not get sufficient material in there. Well, then we heat up more, it becomes more and more liquid, less and less viscous, and it works well. But eventually, of course, we get T too high. And then we get a thermal decomposition, so we damage our polymer. Well, and similarly, expand this a little bit. Similarly, we can vary the pressure, and we already discussed that the pressure can change the swelling behavior. So if our internal pressure is too low, then we may have too much shrinkage. And then we increase our pressure more and more, then we get our shrinkage under control, so more and more following our whatever specifications we may have. But if we overdo, eventually the pressure, or there's so much pressure that it cannot really, the extruder cannot really operate functionally anymore. And then we create what is known as a flash, and that means that the polymer just pops out in an uncontrolled way. It's a little bit like a garden hose that you turn up too much, then it just sprays and it starts to randomly extrude. And now these parameters give you this is known as the moulding region. so an operation space where you fulfill all the criteria, check all the boxes, and then expect to have very good parts. And this, of course, is a function of the polymer you're using, or a very precise function of the polymers you're using. So when you change your extruding machine to a different polymers, then you need to re-engineer your process in order to find these good parts. Okay. So this is also what you see here. And now just to give you an impression of how injection molding works in real life, this is just some images I found on the internet of the fabrication of Lego bricks. So here you see the molding unit of the Lego bricks. So you see here, this will be these 8 boxes, so the typical Lego brick. And what you need to imagine is that the second form will now come from here, push these things together, and then bring them out again. And here we see all the mechanics that can move back and forth. And indeed, if you then look for the other structure, you see here, still a Lego brick in here, and there you have these different forms. And you see that in here, you can encode your different draft angles in order to get these things out very efficiently. Okay, so much for injection molding. Let's move on to the next topic. This is blow molding. And blow molding, as we already said, is how we make plastic bags. And again, the principle is fairly simple. This is what I gave you here. You have a polymer that is relatively soft, like a chewing gum. And what you then do is you blow in air, and this then creates the object you want to create. So the fundamentals of blow molding is very simple. We create an object either by extrusion or by injection molding. And then we heat this preform that we have either again, or if you want still, above the glass transition temperature to ensure that it's soft and malleable. So you can only extrude a chewing gum when the chewing gum is very soft. Just imagine the chewing gum was a Lego brick, then you can blow in air as much as you want, it will never expand. So this is exactly the same thing for any other polymers as well. So you need to make sure that the polymer chains can move, otherwise you cannot reform them. Then you blow in hot air to expand the preform into a hollow container, so a desired shape. This will fill out the shape and thus create your structure. And now there's 2 processes that can do this. You can either use extrusion, then it's known as extrusion blow molding, and in this case you directly convert the polymer tube into hollow containers. So if you want, it's a continuous process, and while your polymer is being extruded, you clamp on different materials and then create these containers. Or you do injection stretch molding, where you do a 2-step process. First, you use injection molding to make a preform, then you let this cool down, bring it to a different machine, and this then re-expands the material and creates, let's say, a bottle. Now you can think about it for yourself, which one is more time efficient and cheap, and why. So first think about this. Well, most likely the extrusion blow molding, because it's a single-step process. And now, second question, why would then anybody care to use injection blow molding? What is the advantage of this process? Well, sometimes you want to only partially inflate materials. For example, if you want to make a screw cap. Now, in your plastic bottle, the screw should not expand because it should still be hard and kind of defined, while the rest of the bottle will be expanded. And then you need to do this 2-step process and follow this injection stretch molding. Okay, how does it look like? This is the extrusion blow molding. So you see here, we have our mold, a blow pin where the air comes in, and an extruder. So now this goes through the extruder. While it goes down, these things close. You blow in air. The air fills the entire, or pushes the polymer into the form. Then you release again, and then you do it over and over again. So the advantages, as already said, very fast. You can make a few hundred bottles per hour. You can make the shape however you want. It's cheap and a 1-step process. So this is very often, if you have these cheap plastic balls, for example, or if you go to IKEA and play in this ball bath, and if next time you do this, take a closer look at the balls, what you will see is that they all have a scar round about the equator. And that scar comes from these 2 spherical units that push the thing together and then create a scar here and here. So this is a telltale sign of a ball or a spherical object that has been produced by this extrusion blow molding, known as the pinch-off scars. So sometimes if you have larger containers, you may need to trim the excess plastic. You cannot do any neck engineering, as in a screw plastic bottle, and you have the scars. So if you want to be more precise, then you need to go for injection blow molding. And here, as I said, it's a two-step process. First, you have your injection unit, and then you create a very short and small mold that contains your screw, and now a non-inflated preform that will form the plastic bottle. Okay, so then you heat it again above the glass transition temperature and blow air in it. So this is what you see here. You heat it up using infrared light, for example. Then you put it into your mold. Then you insert a unit that will blow air in it. Now the polymer expands, follows the form, and then it opens and you eject the final bottle. So you see that now the stretching creates a plastic bottle, but you do not interfere with the shape of your neck, so you can really make a screw cap. So what do you gain? You have a very high tensile strength. You can have very good barrier properties. So for carbonate drinks, for example, sparkling water, it can be very clear. No, this is typical for these plastic bottles. And very typically what you use is PET, polyethylene terephthalate, for carbonated drinks, for your whatever, Coke or Sprite or Pepsi or water, soda water, tonic water, and whatever. So this is how it looks like in real life. This is a picture of a preform. You see here is the screw cap, and here is the non-inflated form. And now if you inflate this correctly, now in this publication, it's put upside down, but you see here, this used to be this part here, and now it has been inflated into this water bottle. And when you have defects in your preform, so you see here, apparently the material started to crystallize. Why do I know that it's crystallized? Think about it for yourself a little bit. Little hint related to the color. So we see it became opaque, and opaque means that there must be two different refractive indices, and this is a telltale sign that it can have crystallized. Then suddenly it doesn't work so well anymore, and you see this poor form just doesn't fill up completely anymore. And the reason for this is also clear. In a semi-crystalline material, even if you heat above the glass transition temperature, it cannot expand completely because the crystalline parts keep the mechanical properties intact and they do not disintegrate until you heat much higher. So you need to avoid this crystallization in order to get a uniform expansion above glass transition temperature. Okay, so much for the production of plastic bottles, and now to the final topic of today, and this is thermoplastic foam injection molding. So here, this is the way on how we make mattresses and bicycle helmet and polystyrene and so on and so forth. So the principle is actually fairly easy. We generate a form via a normal melt process, and then we convert the polymer into a foam within this form, and this then, of course, creates a foamed or a foamed form. So how do we bring a foam into a polymer? And this is something I want to recap with you on the slide, but to do so I need to clear up some space. And while I do this, you can already think about if there's anything you remember from the lectures in the past where foam or foaming was already somewhat an issue or discussed and so on. So how to create forms? There's two options. Let's first start with the one that we have not discussed yet. So you have a bit more time to think about what we already discussed. The first one is a mechanical process. So to understand this mechanical process, let's go back to the example of a chewing gum. So in order to make a chewing gum, we need to have a soft polymer. Otherwise, as we already established, it cannot move. So it needs to be above the glass transition temperature. And now we need to blow air in. Now, of course, blowing air in always creates kind of a directed motion. So we need to now replace the air that we blow in by something else. But the key is that air is a gas. So now we need to find something that produces a gas on demand in our polymer. So what we do is, or the key is, that we blow either a gas directly, or even better, maybe a liquid with a very low boiling point that remains as a liquid, but then as we heat up, it will expand. We call it low boiling point liquid. Let's not call it inserted, but call it incorporated. So how do we do this? First, the polymer needs to be somewhat liquid in order to mix with that liquid, or needs to be malleable. So first, the polymer needs to be above Tg. But the problem, of course, is that the gas or this low boiling point liquid needs to remain in the polymer. So in order to ensure this, we apply a high pressure so the additive stays in the material. So then we can either cool down to trap the material in there, or we can simply release pressure and then it expands. So we form our object. And we release pressure. And now, importantly, how do the polymers need to be while we release the pressure? Well, the chains need to be able to move, to expand, to form the foam, so it needs to be above Tg. And this then results in the foaming process. Now, because the additive that was trapped in there now can go out, and this then allows you to really inflate your material. So what's the second process? We can do it mechanically, we can also do it chemically. So the key is we need to somewhat incorporate a functional unit that can be converted into a gas upon a certain trigger. It can convert into gas And this should be triggered by a chemical reaction. So now, if you think back to a long time ago, in the beginning of our course, we had exactly such a polymer that could undergo this. And that polymer was polyurethane, or PU foam. Does anybody remember how this worked? We had our functional group that looked like this. This is an isocyanate. And we saw that with traces of water, this could convert into an intermediate form, and this directly then rearranges into, so the hydrogen goes to the nitrogen and CO2 is released, and then we create CO2. And here we have our gas that will then form up our material if once we insert traces of water in our extrusion process, or when we look at this, this foam, construction foam, then it comes automatically from humidity. And this is often used to make matrices. Okay. So here you see the same things. And just to show you again how this mechanical process works. So we have our first extruder. Here comes in the mechanical, the crude material. And here comes our foaming agent, so the additive. It's pumped in, so you increase the pressure. That now this forming agent is dissolved in your polymer. And since the forming agent typically decreases the temperature, you decrease the viscosity. So you typically have a second extruder that you control to control for the mechanical properties and the viscosity of this composite material. And now, as it goes out of the extruder, the pressure drops. As the pressure drops, the forming agent is released, and then you extrude a foam. But of course, you can do the same thing in an extrusion unit, and then in an injection molding unit, and then you form up your material by injection molding. Okay, so final thing I want to discuss with you today is Styrofoam, which is, if you want, the archetypical foam material. And here we go back to the blackboard and recapitulate what needs to be done to make Styrofoam. So again, I need to clean up. And you can picture in your mind how Styrofoam looks like already. So if you think about Styrofoam, we think about a white material, think about why it is white, and it consists of individual kind of spherical or close to spherical, if you want, small entities. Now, and we all know this, if you have something from Styrofoam and you break it apart, you have all these small beads flying around, and it's a mess to clean them up again. So apparently this comes from a powder. Now the question is, how do we convert a powder into this Styrofoam? And Styrofoam, as the name already indicates, is made from styrene, or to be more precise, from polystyrene. So what we need to now clarify is how to make the polystyrene in a spherical form, how to make it expand, and how to merge it together, or these expanded beads, how to merge them together. So let's start with number 1, how to make the beads. So in this case, we use a process that's known as suspension polymerization, which is similar to emulsion polymerization in the way that it's conducted in a liquid phase, but we do not rely on any micelles and any diffusion and so on. We simply make monomer droplets and we polymerize these monomer droplets. So we have our reactor, we stir, we have our monomers in here. The monomer is styrene. And while we do this, we add pressure. And as we increase the pressure, we add pentane as a forming agent. So it mixes with the styrene monomer, but we want to ensure high pressure to make sure it stays in the beads, no, because it has a very high vapor pressure. So now we also, by the way, add an initiator. I just indicate this here, but I do not want to go into details about the chemistry. It's a simple radical polymerization. You now initiate and you form a PS bead. So now T is high and P remains high, and this still contains pentane. And simply because the pressure is high, the pentane stays in there. And now we cool down and we remove our continuous phase, and then we end up having hang on, so first maybe we cool down, and as we cool down, the temperature is smaller than the glass transition temperature of the polystyrene, and that means that we efficiently now trap the pentane within our hard material. And once we have this, we can remove the continuous phase. Typically this is water, no, to make it a green process. And then we have our polymer PS beads, and they all contain pentane, so loaded with an additive that can expand. And this is what companies then sell as the crude product to make polystyrene. And the dimensions here of these spheres are approximately 1 to 2 millimeters. So depending on your point of view, either very large if you're used to nanoparticles, or fairly small if you're used to bulk materials. But now these you can simply buy in a big bag of plastic. And now we need to see how this is converted into your styrofoam. And now I don't have so much space anymore, it doesn't matter. So first, now we have our powder. Which is the one that we just bought. So first we want to make sure that the powder becomes a foam. So now, in the new company, we increase the temperature, but keep the pressure at ambient pressure. That means that now we go above the glass transition temperature, and that means the polymer becomes soft, the pentane can escape, and by this foam up the polymer. And the pentane, at least partially, escapes. So now we have our puffed up polymer particles with maybe a little bit of pentane remaining, or also not, just foamed up materials. And now we fill it into a form. Fill it into a form. Compress in the way that we want. So here the temperature can also go down again. It doesn't really matter because now we have this puffed up very soft and lightweight material. We fill it in the form and we increase the temperature again and push together our form into the desired shape that we want. And as we do this, we now partially sinter together our polymer or our polystyrene beads. Sinter or we fuse them, and we do this again using a temperature that is larger as Tg or roundabout Tg to make sure that these polymer beads become sticky without completely melting or becoming liquefied into a solid material. And if we do this, the beads fuse and we have our polystyrene or styrofoam made out of fused expanded polystyrene beads. Right. Here you see this again. So same thing, we synthesize our particles, we add pentane under pressure, we then cool down to trap the pentane, and then we have these pentane-filled beads that we sell, and then we expand again, and we fill them in a shape, and then we fuse them together to form polystyrene. And here you see this again, and this is at the end of the day how the polystyrene looks like. Okay, and with this we are at the end of today's lecture. So what have we learned? Just as a little recap, we discussed pretty much entirely in the lecture how do we get from a monomer to a product, and looked at the process chains and saw that it requires much more than just polymer synthesis. And then we saw that there's a really large range of processing technologies are available, and today we just discussed the very basics, and these very basics were extrusion, injection molding, blow molding, and if you want a bit the specialized way of making foamed materials by adding and releasing forming agent. And with this, I'm at the end of the lecture. I thank you very much for listening, and I'm looking forward to see you next week. Goodbye.